Most recently, I've been at 5G Networks, working on our international MPLS network and our data center fabric, as well as some other fun stuff like automation, documentation cleanup, and process improvements. In my spare time, I enjoy having a laugh with friends, some of which you may know pictured on the right, playing video games, and solving problems with code. For those in the room that haven't heard of us, no, the 5G doesn't stand for that 5G. Still getting messages about it all the time. 5G Networks is an ASX-listed telco with a full suite of traditional services, operating an MPLS network spanning the coast of Australia, all the way from Brisbane to Perth, as well as extending to New Zealand, Singapore, and the United States. On top of your usual culprits like transit and intercapital services, we operate an optical network to underpin this connectivity, offering wavelength services on major domestic and international routes. We also have our own dark fibre network in Sydney, Melbourne, Brisbane, and Adelaide, connecting into our own data centre facilities. As part of our stake in AU Cyber, we also have a bolstered cloud and managed services offering, as well as bringing cybersecurity into the folds of our product set across the broader group. One thing we've been wanting to tackle for a while is a refresh of our data centre networks. There is a lot internally that relies on them, and we want to ensure that as we upgrade the rest of our core network, this is not left behind with legacy solutions and hardware. We have 3 sites we use to deliver diversity, which has worked well for us. However, there's a few challenges we've been facing with the existing solution. The existing network is running Juniper Networks QFX 5100 series switches, which I'm sure is a pretty common choice over the years with many other operators in this room. They have been quite reliable and they did everything we needed when they were selected. However, they have been marked as end of life from the vendor, and we need to start looking at longer term solutions to ensure that we have hardware and software support. Secondly, being an older design means that there's some older technologies at play here. Spanning tree has its place. However, there is newer kids on the block that bring a lot of improvements. This network is using MSTP to try and help better utilise all available links. However, I'm sure I am preaching to the converted here that there are better options in a modern network. Now, let's look at how we work on these devices day to day. Adding an existing VLAN to a port is pretty straightforward. But what about adding a new VLAN? Whole different ballgame. There are lots of pairs of switches in the data center networks, and having to go around and make changes on multiple devices introduces room for error. This results in general moves, adds, and changes being tedious and time-consuming. How are we handling high availability for the endpoints? 2-member virtual chassis clusters are in use, and this does work. It makes bringing up a new lag relatively straightforward. However, who here has had to replace a member of a virtual chassis before due to a failure? It's not fun. You can do everything right and the stack still falls apart. This poses an even bigger risk as time goes on, as the hardware starts to exit the bottom of the bathtub curve and the chance of failure increases. And even when things are running as expected, how can we assure that no bundles have members down? How do we know that a VLAN isn't missing on a backup link? How can we know that we aren't just one wrong move away from having an outage to one or multiple parts of the fabric? Legacy SNMP monitoring solutions work well for individual data points. However, this often takes a good understanding of the design to be able to piece something together and isn't able to cover all the things we would like to see going forward. Finally, these points stick across all 3 of the fabrics. However, the underlying design is often quite inconsistent between them. This makes troubleshooting issues quite difficult for staff that aren't across the intricacies of the design for each site, and this is something we'd like to fix in the new solution. So, how are we going to solve this? Well, put simply, out with the old and in with the new. We decided the best way to modernise our software stack was to first modernise the hardware stack. I'm sure that most people here have had some battles with spanning tree over the years. We knew there was a better way that had emerged since the old network was built, and that is VXLAN. Why switch when you can route? As a team of engineers that love label switching, this is a pretty easy argument to win. Couple that with EVPN for signalling, you've got a great stack that is well supported by many vendors. To solve the issue of differing designs, we decided to pick something rather simple and straightforward, which we could expand on as required. This ended up being just a simple leaf and spine deployment, rather than just a pair of switches with redundant interlinks, to allow us to add more switches as required. We decided to stay with Juniper as our vendor of choice for the network, as Junos is what the team is familiar with across not all of our networks, not just the existing data center network, such as our MPLS network. The QFX 5120 series was chosen as the leafs, and QFX 5200 series chosen for the spine. For automating the network, we just settled on Juniper's Apstra platform. It is quite feature-rich, and we found it to be very useful for assisting in the stand-up of the fabrics. There's some great functionality in there too, for automating the allocation of prefixes and ASNs for the eBGP underlay, as well as for VNIs for the individual networks. As part of Apstra, we also get great telemetry streaming without any additional configuration. This is something we've been wanting to dip our toes into for a while with other parts of the network. So starting with the data center fabric made a lot of sense. Apstra gives us pretty much everything we want out of the box, and being an intent-based solution, it can correlate most of the issues for us and provide a root cause, which without needing someone to dig through the logs and make sense of what is going on. One thing that often isn't clear to a lot of people doing their first deployment of a VXLAN fabric is that not every device can perform well in every function. It's kind of like how a lot of chipsets can support MPLS. However, things like maximum label depth can vary drastically. In our use case, the 5200 boxes are cheaper for flat 100 gig connectivity as opposed to the comparable 5120 variant. However, the Broadcom Tomahawk ASIC on the inside doesn't work that well in the leaf roll. For frames that are already encapsulated with VXLAN and do not require de-encapsulation, however, it's rather well suited. Limitations like this is something that is a little hard to wrap your head around at first, and the vendors often don't do a great job of making this clear. Thankfully, our Juniper SE helped us down the right path. However, not everyone has access to someone at their vendor of choice, especially if you're deploying used hardware. I've had a few discussions with other people in this room over the years about what box works in what role, as they've had exactly the same questions, and I generally point to these two links on the screen from Juniper. There's a good list of what boxes work in what role, and even if your device isn't covered, the second link has the majority of chipsets that you would use for something like this, with the roles they perform best in, and then you can work backwards from there. What about connecting it all together though? Well, layer 3 connectivity comes from our existing provider edge infrastructure on Juniper MX series routers. The other side of the point-to-point connectivity goes over a pseudo wire using VPLS to our label edge routers, running on Ciena's 5000 series routing platform. We are using Martini-style VPLS instances, so there is a targeted LDP session between the PE and the LER to facilitate these connections. We have been deploying the majority of our transit and Alpha VPN services this way for over a year now, with all LER provisioning handled by Ciena's Navigator Network Control Suite platform, and we have been very impressed with the solution. Across all of this, we can connect devices from outside of the fabric to devices behind the fabric in a way that provides a high level of redundancy. We can also use this to deliver DC to DC connectivity, as well as internet connections to our firewalls, which are clusters of Fortinet FortiGates. So, we've got our design all sorted. Now it's time to implement it. The data centers we are deploying this equipment in happen to be facilities that we own, so our ranging for racks and power is all internal. Once these are all ready, we have staff on site to unbox all the equipment and install it for us. One thing we made sure to do from day one was provide out-of-band console access to the equipment, so that we are always able to access the terminal no matter what happens. We have quite a few OpenGear devices using third-party circuits deployed across our network, so we can extend some connections from these back to the devices in the new racks. In the diagram on the right, you can also see that there is a management firewall at the bottom, which is another separated network we have spun up with internet access to ensure that we have another path in alongside our out-of-band console access, as well as for connectivity to management and monitoring tools. As part of providing that management and monitoring access, we have built a temporary L3 VPN to connect the firewalls at the data centers together, as well as to leak some routes in from our existing management VRF, so we can connect back to our existing systems and tooling. So, now we have remote console and data access to the devices. This makes updating them and applying some basic configuration pretty straightforward. It's at this point we also take the time here to update our internal documentation, build some diagrams like this, add the prefixes and IP addresses to IPAM, and add the devices into our monitoring system. The firewalls need some way to learn the routes from the internet and the internal connectivity VRFs though. Just build some static routes and call it a day, right? No, please no. Dynamic where you can, static where you must. We're using BGP to provide the routing information with a session per role, being internet and internal and per PE. This gives us a total of 4 sessions to play with on the FortiGates per IPv4 and IPv6 address family for a total of 8. We have 1 PE in a primary role and 1 in a secondary role. So we use traffic engineering here to prefer one of the links at all times and only fail over when necessary. There's more than ample bandwidth available on a single link for this network, so we aren't needing to use both links at the same time. I'd love to use both links at the same time, however, we're at the mercy of the firewall vendor here. as the connectivity between the FortiGates and the Juniper MXs is only logically adjacent and not physically adjacent, we decided that BFD was the best way for us to handle signaling down the logical link. This is running on 100 millisecond intervals with a multiplier of 3, as in our testing we weren't seeing any noticeable hit to CPU load. As we are leaving BFD to handle the heavy lifting of tearing sessions down, we have left all other BGP configuration, such as timers, to use the platform defaults. The firewalls have their own small aggregates on public IP address space. They advertise back in using a private ASN per cluster and VDOM, and the respective sub/24 and /FortiGate IPv4 and IPv6 allocations only live within our public ASN. We heavily utilise BGP communities to control our internet VRF export policies, with our policies looking for specific matches before allowing a prefix to be sent to another network. This helps to ensure that we aren't externally advertising these smaller routes out. However, in other parts of a network, this also ensures that we don't create route leaks of prefixes with an AS path that we aren't authoritative for. So, we're all good to go. One of the things we decided to test first was the external connectivity out of the fabric. Seeing that we're gluing pseudo-wires and VXLAN tunnels together, this is a good candidate for where something can go wrong along the way and break connectivity, likely from human error. So, let's simulate the human error. As all the switching configuration is handled by Apstra, we can just remove the VLAN from the blueprint to simulate this scenario. This won't signal anything to the devices at either end. Being our routers and firewalls, it will just drop all frames, which is exactly what we want. So we decided to start testing with the primary service. We've enabled some other features on the FortiGates to evaluate multiple possible interfaces when building a session, so that if we fail over the external connectivity to the backup path, little to no packets should be lost as the session isn't needing to be rebuilt. Time to test. We open up Apstra, remove the VLAN and hit apply. We wait a few seconds, and not a moment after we see the configuration being marked as applied to the switches, I lose my in-band web UI session to the FortiGate. We'd also been running ICMP to the firewall, ICMP testing to the firewall, and a host behind it. Both are no longer responding now. He's dead, Jim. Well, that was a little bit unexpected. Okay, time to get onto the console port of the firewall and see what went wrong, because surely it's not my Trio boxes. Open up Lighthouse, find the open gear the active firewall member is plugged into, connect to the port, and before we can even go any further, ICMP messages start being replied to, and my HTTPS connection restores. Clearly that broke something, but then it fixed itself? That's a bit weird. Let's go digging further. We decided the best way to do that is to roll our changes back and see what happens. The firewall doesn't skip a beat. Not a single packet lost on our testing. Interesting. Double check interface graphs, and we've definitely switched back to the primary circuit. Okay, let's give it another crack. But this time we're on the console port of the firewall and poking around at what is going on. We drop the primary circuit, and once again the firewall just stops responding to all external connectivity. We check the BGP session for the circuit we're playing with, and it is down, just like we would expect. BFD seems to be working here as expected. Interesting. Everything else looks fine. Nothing is jumping out as unexpected. So we decide to change tact and look at the MX terminating this circuit. So we log into the Juniper, go looking at the BGP session, and it is still showing established. Okay, so what's BFD doing then? Wait, it just hasn't torn down at all. There's clearly no messages coming in. The VLAN that trunks back to the pseudo wire for this circuit doesn't exist on the switches anymore. So we start digging through the logs. And once again, just as we start to look further, the firewall just reappears and starts responding again. We check the BFD session again, and it's now down. It quickly becomes pretty clear to us that because the primary circuit still has routes installed on the MX, despite the other end not being reachable, the traffic is just being black holed until the session gets torn down and the route's removed. So now that everything's working again, we fail it all back, and once again there is no drops to connectivity. A little bit of playing around with the BGP session, and we can see that if we cleanly signal down the session, it results in a clean failover with no discernible traffic impact. The conclusion here is that any maintenance works or configuration changes that actually tell the other end to take action will work as expected. However, if we are relying on BFD at all, then we are up a proverbial creek with no paddle. It is agreed that this is definitely a bug, and we need to take next steps. Time to engage the vendor. This is the part where my slow descent into madness begins. Please keep your hands and feet inside the vehicle at all times. It's going to be a bumpy ride. Here's the log message that starts it all. We see the BGP session go down due to timeouts exceeding, which is completely fine if we didn't have BFD turned on. However, we do. But then we see BFD go down after it, and what's the message? Received upstream destroy session. So BFD is staying up despite getting no messages. BGP tears down due to timeouts, and then BFD follows suit, as the session it was attached to is just now gone. That's clearly a bug. Surely we won't have to explain that, right? That would be too easy, wouldn't it? So I hop on a call with the engineer assigned to our case, spend over 2 hours explaining our architecture and use case, reproducing the issue multiple times, and answering all their questions. This is all recorded by the engineer for them to come back to as needed. All the tracebacks, log dumps, and terminal scrollbacks are also added to the case to further assist with diagnosing the cause. So surely we're done for troubleshooting here, right? And the issue is clear. One can only dream. We wait for a few days, and then TAC come back with this gem. Our MX's side BFD is single hop. FortiGate BFD is multi-hop. They've also highlighted the multi-hop data as well in the seamless and unknown sections. Right, we're clearly on different pages. No multi-hop here. And not to mention, their notes are also saying they couldn't get a configuration like this to work in their lab. No issue with bringing up the BFD session, all the problems are with tearing it down. For the eagle-eyed amongst us here, yes, that multi-hop bit is set to 0. And yes, the only other option that was highlighted with bits that aren't set at 0 is option 261. And that hex data equals 3784 in decimal, which is the single hop BFD port. So we push back. Multi-hop isn't here at all. The configuration on the FortiGate was also shown to the engineer on the recorded call, and there clearly wasn't anything to do with multi-hop in it. So, what's next? You guessed it, we're once again told that multi-hop is the cause here, and we need to enable it on our MX to bring up the BFD session. So at this point, we decided we're getting absolutely nowhere and pushed for an escalation to a higher level team. And our escalation was successful. Awesome. After a few questions back and forth to understand the case, the engineer sends us this output that they found. We see that the BFD daemon stops responding, the BFD daemon stops seeing messages. However, it doesn't log anything about dropping the session and keeps on transmitting messages. This is exactly the behavior we have been seeing. And the session stays marked as up on the MX. And these transmitting messages continue until our usual BGP down message, followed by BFD being torn down because it has nothing to attach to. The process of engaging engineering is started, and we're assigned a PR number. Success, we're moving forward. A few more questions, along with some more in-depth logging and PFE dumps, and we get the news we've been waiting for. The vendor has managed to replicate our issue in their lab. Right, let's just wait for a few days and see what happens. Hopefully this is related to something that is already fixed, and we can just upgrade to resolve the problem. We've waited patiently, and hopefully we have some good news. We can get this to work by adding a dummy physical interface to the VPLS instance. Oh. So we push back again, and we ask to see what else we can do here, as that's a little less than ideal. Their response says that if they believe we can just turn off hardware processing for BFD on the whole device. Not moving it all onto the CPU, and that will fix our problem. Alternatively, if we wanted this to work in hardware, we need to get an enhancement request raised up to the PLM for evaluation to add support. That's quite disappointing. We have some physical interfaces we are also using BFD on. We're going to need to see what kind of CPU impact we're talking about here before we make any decisions. So we get ready to start testing removing the hardware offloading for BFD. But before we can even get a chance, TAC comes back that this fix doesn't even actually work. Well, thankfully they sorted that fast before we spent any more time on this. To this point, we're getting into the later part of December, with the case having been open now for around 2 months. So we start to wind down for the annual telco shutdown period and pick back up where we left off in January. When we come back, we find that our TAC engineer has been hard at work over the break while we've been enjoying our holidays off. We come back to see that they have a fix for our issue. Just restart the PPM daemon. That's a pretty impactful thing to be doing. However, at least now we're feeling a little more sane that what we were trying to do isn't some crazy thing that the box couldn't handle. So we leave TAC to continue looking at what the cause is and see if they can get a software patch in to resolve it. Or maybe we actually don't need a software patch at all. It actually only is if the PPM daemon gets restarted just once, either manually or as part of a reboot, the issue is fixed. We're only hitting this issue because we are on our first boot after upgrading to this Junos version. TAC are advising they are unable to reproduce the issue either on their newer internal builds. So it sounds like we're getting closer to a resolution here. We're hitting this behaviour on 21.2 code, which we've been working towards upgrading before hitting this issue. So we upgrade a box to 23.2 train, and sure enough, the issue isn't visible anymore. Roll the software back to 21.2, reboot into it, the issue reappears. Reboot the box, issue is now gone again. I was actually stunned, completely sceptical of the solution TAC had provided up until this point. Surely engineering know what they've done to fix this though, right? No, apparently they don't. Looks like there's a few other teams involved here that are all pointing their fingers at each other. We wait to see if we can get any more information as to what the cause is. However, that answer just isn't clear. We'd like to have something to refer to for this bug, however, for documenting internally as well as being visible for others potentially hitting the same issue. So we ask for either our PR to be made public or for a KB article to be created. Seeing that we had been just told they have no idea how they fixed the issue, just that it was fixed, I did expect a little bit more pushback on this. But we got our knowledge base article, immortalised on the internet. Want to fix this issue if you hit it? Restart the PPM daemon or reboot the box. Fixed, gone. Won't come back on the software installation you're running. This bug only affects the first boot on an affected version, which had never even occurred to us that something like this was possible before going down this rabbit hole. Surely, after upgrading a device and it boots into the OS, it should be the same as every subsequent boot. Apparently that isn't always the case. The article mentions that only 21.2 R3 S2 is known to be affected. Is that the only version impacted? We don't think so. And the final line sums up why we believe so. How issue is fixed in newer release is unidentified. I figured this one would go without saying, however I definitely wanted to cover it. If I have to reboot something after starting it up for the first time for it to operate properly, it's not truly a first boot, is it? As an engineer, you try and look at the facts before doing something drastic. Whatever is going on under the hood here is not something you would expect to encounter, nor is giving the box a kick to permanently fix the issue expected at all. Unless you're a MikroTik user, I guess. There's a few important things we have taken away from this. First of all, try not to leave testing until things are further down the track. Break things early and see what happens. Definitely try and get to it before you have production traffic involved. Thankfully, we did in this case. Secondly, expect that breaking it will fail spectacularly and go looking into the logs and output to prove otherwise. Thirdly, try your best to simulate what a failure could look like in the real world, whether that's someone unplugging a cable, removing a VLAN, or power cycling a device. The more realistic, the more likely you will be to find that something went wrong. Lastly, reach out to your industry peers, many of whom might be in this room, and talk about what problems you're trying to solve and the issues you're facing. There's some absolutely amazing people here, and even if you're just looking for validation that you're not completely insane with an approach to a problem, it makes us all better engineers to learn from each other's successes and failures too. So I'd quickly like to take this opportunity to give a quick shout out to Sohan and Elaine at Juniper for all their assistance on this issue, as well as to the rest of the engineering team over at 5G Networks and the BBL crew for putting up with all my rants about this. I've published this entire talk to GitHub at the link on the screen. Feel free to have a look if there's anything you missed earlier, need any of the links, or you're interested in how I built this deck using Markdown. Thank you.